Welcome students to the next lecture of microcontrollers. So today we will study timers and counters. So as I promised in the lectures where I introduced the special function registers, if you remember, that we will go through the details of the special function registers when we go through the related lectures. So today we are going to learn about these special function registers. Okay, so these are all associated with your timers. So timers are a very important unit of the 8051 microcontroller. So it allows you to generate some delay, or if you are counting some units, or you are let's say you need to operate based on some time intervals with your microcontroller, then these timers come to your use. Okay, so one example will be, let's say you want to open the door of an elevator, okay, after a few seconds. So when you press a button, the elevator door will exactly open after, let's say, 1 second or 2 seconds, and that 1 second and 2 second delay can be generated by the timers that are there in the microcontrollers associated with the elevator operation. Okay, so this is just to give you an example. Usually it doesn't take 1 second to open the door of an elevator, unless it is the elevator in my apartment complex in Dublin, which is very slow, and the door indeed opens after 1 second. So, but just to give you a practical flavor, I just gave this example. The main idea is that whenever there is an operation that involves some delay, or to count something, let's say you want to count the number of goods produced in an industry for one day. So there will be some sensor that will be, detecting the goods that are coming on a conveyor belt, and then there can be a microcontroller with a timer that operates in a counter mode that can count the number of units detected. Okay, so we will get through these examples later during this semester, but let's now start and see the concepts of the timer. So there are these special function registers that are associated with timers, as I just said. So we will also study the functions of these registers and how they are used. So let's move on. So the 8051, it has two timers / counters, because the timers can be configured as counters also, and they can be used as traditional timers to generate a time delay, as I just said, or as event counters to count the number of events happening outside the microcontroller. So I gave examples of both these scenarios, okay, just now. So so both timers, like the timers are named as timer 0 and timer 1. So both timers, timer 0 and timer 1, are 16-bit timers. Okay, so basically this means that they can count from 0000 hex to F fx. So they can count between 0 or so in decibel equivalent between 0 to 65536. Okay, so they are 16-bit timers, but the 8051, it's an 8-bit device. Okay, so this means that two separate 8-bit registers are allocated for each timer. Okay, so the low bytes of timer 0 and timer 1 are stored in TL0 or TL1, and the high bytes are stored in TH0, TH1. So one timer, let's say timer 0, is comprising of two 8-bit registers like this. So let's say we call it TH, so this is TH, this is TH1, so this is TH1 and this is TH0. Okay, so these are two 8-bit registers, and together they form the 16-bit timer 0. Similarly for timer 1 also, I'm sorry. So this is TH0 and this is TL0. Okay, TH0 for the high 8 bits and TL0 for the low 8 bits. Okay, for timer 1 this will be TH1 and TL1. Okay, so TH0 TL0 forms the timer 0, TH1 TL1 forms the timer 1, and both of these are 8 bits. Okay, so these registers can be accessed. So all these registers, this one, this and this, can be accessed like any other regular register that you have come across so far. So let's consider the example here. So let's say if you move this number to TL0 and this number to TH0, then the entire timer 0 will read like this. So TH0 contains your 0F and TL0 contains FF. So the entire timer 0 contains 0F, FF. This is the 16-bit number of the timer 0. Okay, that the current number that is contained in timer 0. Okay, so if you want to load a 16-bit number into a timer, okay, then you break it into two 8 bits and then you load the higher register with this 8 bits and the lower register with this 8 bits. So that's what is happening here. So now let's see the functionality of tmod. So tmod is basically a register that is used to set the operation modes of the timers. Okay, so this is also an 8-bit register and it has the following nomenclature. Okay, so tmod is again divided into two parts. The least significant 4 bits are for timer 0 and the most significant 4 bits are for timer 1. Okay, and then the 4 bits corresponding to the two timers are again classified into different categories. So we will see what are they. So let's start with the gate. So the gate bit determines whether an external source or the software starts the timer. So when your gate bit is 1, the timer is started from an external source, and when the gate bit is equal to 0, the timer is started by the internal software. Okay, so again we will get into these examples when we will be doing interfacing with external devices. So you can interface your microcontroller with an external device, and that external device can start your timer, okay, through these pins, pin int 0 for timer 0 and int 1 for timer 1, okay. And if that is the case, then the gate bit should be 1, otherwise it should be 0, and then that means that a software starts the timer. Next comes this particular bit of the TMOD register. So this, when it is set to 0, it gives timer operation. When it is set to 1, you have a counter operation. So see, the same timer can be configured as a counter or a timer based on whether this bit is 0 or 1. Okay. So these are all the bits in the TMOD register, by the way. Okay, so we have the TMOD register, and that is divided into two parts, as you saw, for timer 1 and timer 0. So this is for, this part is for timer 0, this part is for timer 1, and then you have, these are the bits. Okay, so this is the gate bit and this is this C comma T bit, as you just saw here. So we covered the functionality of the gate bit and the C/T bit. Okay, so now let's see what are these M1 and M0 for. Okay, and this side for timer 1 also you have the same configuration repeated. Okay, so let's see what this M1 M0 means. So M1 and M0, they together define the timer modes. Okay, so if M1 and M0 are 0 0, then you are in mode 0. For 0 1 it's mode 1, and so on. So these two bits can give you 4 combinations, and all of them has some meaning. So for mode 0 means it's a 13-bit timer mode. Okay, so 8-bit from TH0 or TH1 and 5-bit prescaler from TL0 TL1. So this is out of the scope of this module because this 13-bit mode is used for 8048 microcontrollers, which is a predecessor of 8051. Okay, so this used to come before 8051 came. Okay, and this mode 0 doesn't exist for 8051. Okay, it was for 8048, and we are not interested in this mode for this module. So what we are interested in are these modes. Okay, so this is mode 1. This is the 16-bit timer mode. So it uses both the TL and TH registers for a full 16-bit timer. So whether so this could be 0 or 1, this could be 0 or 1. So you have 8-bit here, 8-bit here, and all of them are used as a 16-bit number to be used by the timer. So basically for mode 1 you can count between 0 0 0 0 to F F F F, or in other words between 0 to 65536. Okay, so you can use the entire 16 bits to count. For mode 2 we have this mode which is called 8-bit auto reload. So in this case, your TH0 or TH1, the higher 8 bits, okay, let's say this is TH, this could be 0 or 1. This holds the value, let's say X, which is reloaded with the value in TL0 and TL1. So let's say this is the TL0 or 1, and this value is reloaded here, okay. So that's why it's called 8-bit auto reload. So this is an 8-bit timer, okay. This is not a 16-bit timer as in the case of mode 1. In mode 2, we can count, let's say here the initial number is X, okay. So this is going here from TH to TL, and whatever is the X, the timer can count from X to FF. That is the maximum number that can be counted for an 8-bit timer. And the moment it finishes counting up to FF, it starts again, okay, it starts counting again. Whenever it finishes counting to FF, this value in TH0 or 1 gets reloaded automatically. That's why it's called auto reload. And then it starts counting again from this number to FF. But in case of 16-bit, whatever is the initial number that you load here, okay, it starts counting from that number up to FFFF, and whenever it finishes counting up to this value, then you have to yourself as a programmer reload these two registers by moving the numbers into these registers, okay. So this is the difference between these two modes. We will see examples that will clarify this more, about the differences of these two modes. And then the mode 3 is the 8-bit split timer. So this defines timer 0 and timer 1 separately as two 8-bit timers which can count from 0 to 255. So these are treated as two different timers, both of them being 8 bits, and it's the mode 3 of the operation. So now let's see the TCON register. So in the TCON register, again you have different bits which has different functions. So these 4 bits starting from the MSB towards this direction, these are the timer control flags, okay. So so we will not cover this part now, okay. We will cover this part when we study interrupts, okay. So these are basically interrupt flags, okay. So we will cover these flags in the next section when we talk about interrupts. These 4 flags are the timer control flags. So let's say this TR1 and TR0, these two bits control the start of the timer. So if TRX equal to 1, timer X is on, okay. So if TR0 is 1, then this means timer 0 is on. If this is 0, then this means timer 0 is off. Similarly, if your TR1 is 1, then this means timer 1 is on, okay. and if it is 0, then it means timer 1 is off. So these two are for starting the timer. Then the next two, the TF0 and TF1, these bits are flags that are set when timer 0 or timer 1 overflows or underflows. Okay, so when it finishes counting, when timer 0 or timer 1 finishes counting and reaches the maximum limit, which is F, 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 F for mode 1 and just FF for mode 2, because your mode 2 is 8-bit auto reload. So whenever the timer reaches these values, the timer overflows and these bits are set to 1 whenever that happens. We will see example of this shortly. So as I said during the start of this lecture, so timers are, one of the functions of the timers are to use them as delays. So let's see how can we calculate the delays. Okay. So the system clock frequency in 8051 is derived from the crystal oscillator frequency, and traditionally the system clock is equal to 1/12 of the crystal oscillation frequency. Okay, and we will always assume this to be the case in this course. Okay, so for the CPU to execute an instruction, it requires a certain number of clock cycles. Okay, so these are referred to as machine cycles. Okay, so the next example should clarify this point. So let's see. So find the period of a machine cycle TMC for a typical 8051 microcontroller with a crystal oscillator frequency of 12 megahertz. Okay, so let's say the crystal oscillator frequency, okay, is 12 megahertz, which means 12 into 10 to the power 6 hertz. Okay, so the clock frequency of the microcontroller, let us define that as F clock. So this is basically F OSC by 12. Okay, and one machine cycle is basically 1 over this clock frequency, right? So if you now replace this, you will get 12 over the crystal oscillator frequency. Okay, which is nothing but 12 times the time period of oscillation. So that is what is given here. TMC is equal to 12 times T oscillator, and T oscillator is 1 over F oscillator. So this is 1 over 12 microsecond. Okay, so therefore the TMC is 1 microsecond. So this is the unit of one machine cycle. Okay, so to determine how long it takes a program to execute, we need to just count the number of machine cycles that is required for each instruction, okay, and multiply this by the period of a machine cycle. So let's see an example. So from this example, let's say we have a code like this. So what will be the total delay that is encountered by this code? Okay, so you can individually check each instruction and see how many machine cycles each of these instructions take. So for example, your move instruction and your CPL complement require one machine cycle. So this is one machine cycle, this is one machine cycle. Okay, then a call dj and z and return, these require 2 machine cycles. So this is 2 machine cycle. CPL is 1 machine cycle. Okay, and then here you have again this line 1 machine cycle. How about this line? Okay, so your R3, it contains 200. Okay, so so this line in general it takes 2 machine cycles, but then this loop which is run 200 times because your R3 has 200, so this will be this is again 2 machine cycle, but then this loop here, okay, this will take or rather sorry, this loop just a minute. So this loop, so this is 1, this is 1, this is 2, this is 1, this is 1, this is 2, this is 2, and this loop here, this will take 200 times. So 200 times whatever this instruction takes, which is 2 machine cycles, because this is R3 which is containing 200 and dj and z R3 here means it stays in this line until your R3 goes to 0. So this operation dj and z R3 here takes place 200 times. So this should be 2 into 200. So now if you add everything, you will get a total of 408 machine cycles, and 1 machine cycle is 1 microsecond, so therefore the total delay is 408 microseconds. So the first section of the program takes 5 machine cycles. Okay, so 1 plus 1 2 plus 2 4 plus 1 5, and the delay subroutine, it takes 1 plus 2 into 200 plus 2. So 1 plus 2 into 200 plus 2. So that will be 403. So total, if you add these two, this will give you 408 microseconds. So basically total is 408 machine cycles, and 1 machine cycle is equal to 1 microsecond, as you found in this example here. So therefore you have total 408 times 1 microsecond, so that gives you 408 microseconds. So now let us see if a microcontroller has a crystal oscillator frequency of 20 megahertz, then how will you write a delay subroutine that implements a delay of 120 microseconds? So we can use the same code from the last example as a template for our delay subroutine. So everything remains the same in that code, and then we have an a call delay that takes you to the delay subroutine, and then you have, so remember that the first section of the code remains the same as previous example. Okay, and that used to take 5 machine cycles, right? So if you go back, so that was 5 machine cycles. So this part of the code is same, okay, for this this example. So 5 machine cycles are already taken. Now let's see what's happening inside the delay subroutine here. Okay, so your delay subroutine also has the same structure, but here you have to load a value which you don't know, which you have to calculate based on the fact that you have to generate a 120 microsecond delay. So let's work backwards. So let's say how many machine cycles you need to generate a delay of 120 microseconds. So one machine cycle is 12 over 20 microsecond here, because here you have the oscillator frequency as 20 megahertz. So your T os will be 1 over 20 microsecond, and TMC is basically 12 times T oscillator. So that gives you 12 by 20 microsecond, right? So this is your TMC for this example, and you have to create a 120 microsecond delay. So that means you need 200 machine cycles. So out of this 200, 5 machine cycles are taken off for the first part of the code. So inside this delay subroutine, basically you have to generate 195 machine cycles. Okay. So 195 machine cycles you need from the loop itself. So again, inside the loop you can see, again, out of this 195, 1 will be taken by this and 2 machine cycles will be taken by return. So just this particular loop will require 192 machine cycle. Okay, because 2 are taken for return and 1 for move. So 192 cycles are required by this DJNZ R3. So DJNZ itself is 2 machine cycles, and you have to make 192 out of this. So that means your R3 should be loaded with 96. So that when you do DJNZ R3 here, where your here is the same line, then if you want to have 192 cycles out of this instruction, then you have to and DJNZ being 2 machine cycles, so you have to load R3 with 96, the decimal number 96, so that the multiplication of these two and 96 becomes 192. Okay, so you have to load R3 with 96, and that will give you an overall delay of 200 machine cycles, which is equal to 120 microseconds. So you can also note that we can implement exact values of delays required by adding a no operation instruction just after the call to the subroutine. So this requires 1 machine cycle, but it does nothing else. Okay. So if let's say if you want to adjust this number a little bit, if you want to have a delay that is not exactly matched by the instructions in the code, then you can add some extra instruction that does nothing but adds 1 machine cycle of delay. Okay. So let's move on. So we just saw that how to generate delays using timers, and now we will extend this concept forward. So let's say if you are asked to write an assembly program to create a square wave with 50% duty cycle on a bit 5 of port 1, that is P1.5, then what will be your output? What will be the code? Okay, so the code here is given. Okay, but let us analyze this code one by one. So you can see this code has a main part, and then there is a subroutine here. Okay, so so you are calling this delay subroutine using a call from the main code, and the delay subroutine is basically taking care of the delay. Okay, and see, you are loading your timers with some numbers, and then you are loading the T mod with this. So let's see what does these mean. Let's first focus on the main code. Okay, so the main code is written here again. So let's say the first thing that you are doing is to set the mode of the timer. So you are moving this number 0, 1 to T mod register. Okay, and if you remember that your T mod register has two parts for the two timers. Okay, so the least significant 4 bits is for timer 0, and the most significant 4 bits are for timer 1, and among those, these are the bits that set your mode. Okay, so when you are loading this T mod register with this number, this means 0, 0, 0. Okay, so basically if you focus on this part, your M1 and F0 is 0, 1. So basically you are choosing timer 0 for mode 1. So this part is for the timer 0 part, and you are choosing timer 0 in mode 1 by setting these 2 bits to 0, 1, and that's what you are doing. You are loading the entire T mod register with 0, 1, which means it's loaded with this 8-bit combination, and the least significant bit is 1, which means that timer 0 is in mode 1. Okay, and that is the 16-bit timer mode. So if you are using it as a 16-bit timer, then you have to load both TL0 and TH0 with some numbers, so that together they form the 16-bit number. So here we are loading TL0 with the low byte and TH0 with the high byte. So that means your timer 1, this is timer 0. So your timer 0 contains F, F, F2. Okay, this number. So you are loading the lower byte with F2 and the higher byte with FF. Okay, so the entire 16-bit number that is represented by timer 0 is FF2. So now you call the delay, now you complement port 1.5, because that is the port where you want to see your square wave output. So if you look into port 1.5, your port 1.5, let's say the initial state was 0. If you toggle, then it will be 1. Okay, so port 1.5 will reach to a state 1 from 0. Okay, after this operation, and it will remain in the state 1 for the value of this delay, whatever it is. Okay, and then you are short jumping to this line again, and again the timer will be moved with this number, and the complement operation will happen, so it will move to 0 now. Okay, and it will remain in 0 for the duration of this delay, whatever is the delay. Okay, So in that way you will have a square wave like this as an output of your P1.5 pin. Okay. So now let's focus on the delay part. So what is happening in the delay part? The delay subroutine is using the timer, and here what is happening is that, let's say you have already loaded your timer 0 with F2, right, as you saw. So inside the delay subroutine your timer is first started. Okay, so set TR0 means your TR0 is set to 1 by this instruction, and then your timer will start. Okay, so timer starts means it starts counting from this initial number what is stored in the timer, and it will, at each clock cycle, it will start, it will count to the next number. So it will start at FFF2, then it goes to FFF3 at the next clock cycle, then it goes to FFF4 in the next clock cycle until it reaches FFFF. Okay, so this is the final number that the timer can count in the 16-bit operation. Okay, and for all this situation your TF, the timer flag, is 0. Okay, but once it reaches this state and rolls to the next state, then your timer is overflown. Okay, so the 16-bit timer overflows and the timer flags is getting to 1. Okay, so the moment the timer flag, so you are monitoring the timer flag for the timer 0, which is your timer that is on. Okay, and JNBTF0, again this particular instruction monitors the timer flag 0 until it rolls over. So as long as it is 0, that means jump on no bit. So as long as this is 0, it stays in this line. Okay, it checks TF0 and it jumps to the same line until it has a no bit. Okay, the moment the timer finishes counting and rolls over to this state, your TF goes to 1, and then this instruction is not valid again, so it goes to the next line, which is clearing TR0. That means it stops the timer and then it clears the TF0 and then it returns to the main program. Okay, so it returns to the main program. So now if you look into the entire code, so what is happening is that you are loading the TMOD register with 0, 1, and that sets your timer 0 in mode 1. Then you are loading the higher and the lower bytes into the timer 0 by moving these numbers to TL0 and TH0, so that together they form FFF2 for the 16-bit timer. And then it toggles the pin 1.5. So whatever is the initial state, it goes to the next state. If it is 0, then goes to 1 after this instruction, or if it is 1, then it goes to 0. So let's say the P1.5 is initially 0. Okay, so after this instruction it will go to 1, and then delay subroutine is called, so it goes to the delay subroutine. Inside the delay subroutine your timer 0 is started, and until the timer flag 0 is overflown, it stays in this line. Okay, So that means here you start the timer initially has this value, it starts counting from FFF2 to FFFF, okay. So until it reaches FFFF, it remains here, and then the moment it reaches FFFF, the timer flag 0 overflows, and you stop the timer, you clear the flag and return back here, okay. And when you return back here, it says that you have to jump to this line, and you are jumping to this line where you are reloading the timer again, and then you do the same operation again. So your P1.5 reached to 1 and it stayed at 1 until the entire period of this delay subroutine, and this delay subroutine operates for the entire time as long as it takes the timer 0 to count from this to this, okay. So whatever time it takes, that is the time of the delay subroutine, okay. So and this time is the time it stays in 1, okay. The moment the delay subroutine finishes, it jumps to this line, and then this line makes the program jump to this line, and the timer is reloaded, and then you have this complement. So this 1 goes to 0, and it remains at 0 for another time period, which is the time of the delay subroutine again, okay. And then this operation repeats, and you get a square wave at the output of P1.5, okay. So this is what is happening. So now the question is, how much time delay actually generated? So this depends on the crystal frequency and the machine cycle. So for the code in the previous example, if you are asked to calculate the amount of time delay in the delay subroutine, then the first step is to divide this frequency of the crystal by 12 to get the frequency of the timer. So this is the frequency of the timer. This is basically also giving you the machine cycle. So machine cycle is 1 over this frequency, and that is 1.085 microseconds. So the timer 0 counts up 1.085 microseconds at each count, okay. So when it starts counting from FFF2 as in the previous example, when it goes to FFF3, the next count, it has taken 1.085 microseconds. So then again it goes to the next number, FFF4, so it takes another 1.085 microseconds, and so on until it reaches FFFF. So basically the total time it takes is basically the number of counts times the 1.085 microsecond machine cycle, and the number of times that is counted can be simply obtained by subtracting the initial number FFF2 from the maximum possible count that is possible for this 16-bit timer operation, and that number is 0D in hex or 13 in decimal. So we add, but however we add 1 to 13 because of the extra clock needed when it rolls over from FFFF to 0 and raise the TF flag. So this gives total 14. Okay, so 14 into 1.085 gives you 15.19 microsecond for half the pulse. So you remember, if you go back to this example. So this is your just calculated time interval. So this is 15.19 microseconds. Okay, so this is for half the pulse. This is also 15.19 microseconds, and this is the total pulse width. Okay, one entire cycle of this square wave. Okay, so that is 15.19 plus 15.19. Okay, so 15.19 is for half the pulse. For the entire period, we have twice 15.19 or 30.38 microsecond as the time delay generated by the timer in this case. Okay. So general rule for delays using timers. So you can have in hex whatever is the maximum FF minus YYXX plus 1 times 1.085, where YYXX are TH and TL initial values respectively. Okay. In decimal, you can convert YYXX values of TH and TL register to decimal to get whatever the decimal value is, and then the maximum possible number that the timer can count in decibel is 65,536. So this is basically 2 to the power 16 because it's a 16-bit timer. So 65,536 minus the decimal equivalent of YYXX. So your, let's say this is your TH and this is your TL. Okay, I say it X, THX and TLX. So X can be 0 or 1 depending on whether it is timer 0 or timer 1, and then let's say this TH contains YY and TL contains XX. So YYXX will give you some decimal. So 65536 minus that decimal times 1.085 microseconds is the total delay. So you can calculate it in both ways. So let's see an example. So find the delay generated by timer 0 in the following code using both of the methods of slide 20. So do not include the overhead due to instruction. Okay, so let's see. So your timer is loaded with these values. Okay, so TH0 is this and TL0 is this. Therefore, the 16-bit number is B83E. Okay, in hex. So that is the number that is contained in the 16-bit timer, and it's operated in mode 1. So timer 0 is operating in mode 1, so which is the 16-bit mode, just to verify. So therefore the total delay will be the maximum possible number FF minus this B83E plus 1. Okay, so this gives you 47C2 in hex, which is 18370 in decimal, and 18370 times 1.085 is 19.93 milliseconds. Okay, you can also do B83E, which is 47166 in decimal, and then you have 65536 minus 47166, that gives you 18370, and then you get the same number, 18370 times 1.085, and you get 19.93. So now let's look into this problem from another angle. So let's say you now want to generate a square wave with a given frequency. Let's say that frequency is given to you, which is 1 kilohertz. And you know the crystal oscillator frequency, which is 12 megahertz. So now find out the delay time required and the timer 0 starting values for TL0 and TH0. So in the previous example, you were calculating the delay that was generated. Once you generate the delay for one cycle, so in the previous example, your initial value of the timer was given, right? Value was given, and you were calculating the total count by FFFF minus the initial value, let's say YYXX plus 1, and then you were multiplying this with 1.085 microseconds, right? Now, if you know this delay, so this was the delay. So this was basically the delay for one cycle of the square, one half cycle of the square wave. So this was the delay. Okay. For two cycles, two half cycles or one full cycle, you will have 2 times this delay, which is given by this. So you can calculate the period of the square wave, which is equal to 2 times the delay, right? And if you calculate the period of the square wave, you can calculate the frequency of the square wave, okay? F equal to 1 over t. So now, if you are given the frequency of the square wave, can you find out that what will be the values that you need to store in TL0 and TH0 to give this exact frequency? So you can apply the same concept, but you have to work backwards. So let's see. So the time delay required is very simple. If you have a 1 kilohertz square wave, then the period of the square wave is 1000 microseconds. So you work out backwards from F. You can calculate T, okay? And 2 times the delay is your T. So the delay that you need is actually 500 microseconds, okay? So now you have to make 500 microsecond here, and let's see what is the machine cycle. In this case, the machine cycle is 12 megahertz divided by 12. So the system clock crystal oscillator frequency divided by 12. So in this case, you have 1 megahertz is your timer frequency. So if you work this backwards, then you have 1 microsecond as your machine cycle, okay? So instead of 1.085 for the previous example, we have 1 for this example. So 1, now the delay is basically then 500 microsecond as you worked out from the previous example, and this is 1 microseconds times this FF minus YYXX, okay? So basically your FF minus YYXX will have to be 500, okay? So in other words, if you look into this from the decimal perspective, this is 65536 minus the decimal number n. This has to be equal to 500 according to this, okay? So again, let's revisit. So you can either do FF minus YYXS plus 1 into the machine cycle, or you can do the decimal 65536 minus the decimal equivalent into the machine cycle. Okay, so you use the second concept here. So we will do the decimal number 65536 minus the decimal value n, which we need to find out. That is equal to 500 microsecond. Okay, so 1 microsecond is your machine cycle delay here. So basically this number 65536 minus n has to be 500. So to make this 500, this small n has to be just a minute. Sorry. So you have to count the timer, and the total delay has to be 500 machine cycles. So whatever is the initial number n, okay, so 65536 minus n will have to give you 500. Okay, so your n, so this has to be 500. So you have to find out n. So your n will be this 65536 minus 500, and whatever that number in decimal, let's say 65036, if you convert this to hex, then you get this number FE0C, and then you load your timer register accordingly. So you load the higher byte to TH0 and the lower byte to TL0. Okay, so so this is how you should approach. Okay, if you are given a square wave with a specific frequency and you have to calculate that frequency. So let's revisit this once more. So you have 1 kilohertz square wave. So that means you have 1000 microsecond is the period of the square wave. Okay, and by period of the square wave you mean the time of one full cycle from here to here until it repeats. Okay, so that is the period of the square wave, and the square wave is made of these two parts. So it stays in high for one particular delay, and then it stays in low for the same amount of delay. Okay, so basically your t is equal to, if this is the d, that is your delay, then t is equal to twice t, where d is your delay. And to make this delay, you are using the timer to load some value and let it count, and as long as it counts, it generates this delay as you saw previously. So basically in this case the delay has to be 500 microsecond because my square wave period is 1000. So we have to make 500 microsecond from the timer. So now to make 500 microsecond from the timer, which has one machine cycle of 1 microsecond according to this example, because of this 12 megahertz oscillator frequency, so you have to count 500. The timer has to count 500 cycles. Okay, so to make the timer count 500 cycles, what number you have to load, that you can find by this. So if your timer starts at a value n, let's say, and it can only count up to 65536. So 65536 minus n will give you the number of cycles. So this is 500 in this case. So you can obtain n as 65506, and this is equivalent to FE0C hex, and that you load into your TH0 and TL0. So the higher byte is stored in TH0 and the lower byte is stored in TL0. So let's do another example. So assume your crystal is now 11.0592 megahertz. So you have to write a program to generate a square wave of 50 kilohertz frequency on pin 2.3. So you can do this by, let's say, calculating the period of your square wave first. So since your square wave frequency should be 50 kilohertz, so the period is 20 milliseconds, okay? And the delay that you need to generate is half of this time, so that is 10 milliseconds, okay? And if you have 11.0592 megahertz crystal frequency, then each machine cycle will be 1.085 microseconds, okay? So to make 10 millisecond from 1.085 microsecond per machine cycle, the number of machine cycles you need is 10 millisecond divided by 1.085 microsecond. So these many machine cycles you need, 9216. So if you now deduct this number from 65536, then this is the number in decimal that you need to load in your TH0 and TL0. So if you convert this to hex, this is DC00. So you load your TH with DC and TL with 00. So this is your final code. You can either operate with timer 0 or timer 1. So this example shows you with timer 1. So you are loading timer 1 with mode 1, that is the 16-bit mode. So you are loading 10 in T mod, and then you are loading TL1 with 00 and TH1 with 0 DC, and then you start the timer, and then you monitor the timer flag until it rolls over. Once it rolls over, you clear TR1, which means you stop the timer. You complement the pin 2.3 where your square wave output should be shown, and then you repeat the entire operation, okay? So you can do the same thing with timer 0 also. In that case, you have to do load T mod with 01 hex, and then this should be 0, this should be 0, this should be 0, this should be 0, this should be 0. So you can choose any of the timer and you can write the code. So let's do this exercise. Write an assembly program to create a wave with 10% duty cycle and frequency of 500 Hertz on bit 5 of port 1. So I will give you some time. You can pause this video here and work this example out, and then you can share your code with me in the live interactive sessions, okay? So let's go to mode 2 programming. So far all the examples were for mode 1, that is the 16-bit mode. Now let's see how the mode 2 works. So the following are the characteristics and operations of mode 2. So basically it is an 8-bit timer. Therefore it allows only values from 00 to FF, okay? The first characteristic is this. And the value that you are loading is loaded to the TH register. So if you are working with timer 0, you load to TH0. if you are working with timer 1, you load to TL0, okay, and you load an 8-bit value to this register, sorry, TH1, sorry, this should be TH1, okay. So so you load an 8-bit value to the TH registers of the corresponding timers with which you want to work with. So after the TH register is loaded with the 8-bit value, the 8051 gives a copy of it to TL, okay. Then the timer must be started. This is done by setting this TR0 to 1 for timer 0 and TR1 to 1 for timer 1. After the timer is started, it starts to count up by incrementing the TL register, okay. So so your TH0, let's say, contains some value, okay, X, and then it gives a copy of X to TL0, okay, and then the timer starts counting from X to X plus 1, X plus 2 and so on until it reaches FF, okay, until it reaches the limit of FF, and when it rolls over from FF to 00, it sets the timer flag, okay. So once it goes to 00 from FF, the timer flag is set to 1, okay, and the moment the timer flag is set to 1, that is when your TL register rolls from FF to 0, TL is reloaded automatically with the value kept by the TH register, okay. So so your TL, let's say, rolls from FF, so let's say this is your TL, it rolls from FF to 00, okay. The moment it does so, your TF flag, your TF flag is set to 1, and then your TH, which was containing X, reloads this X here, okay, and it becomes X again, and then it starts counting again. So this makes mode 2 an auto reload mode, okay, in contrast to mode 1 where the programmer has to reload the TH and TL, okay. So this is the schematic of the auto reload mode. So you have the clock frequency here, which is the divided by 12 of the crystal oscillator frequency. So this clock, along with your TR, which is set to 1, runs your timer, and your TL is loaded with some value X from TH, okay, and it starts counting. Once it rolls to FF and goes from FF to 0, the overflow flag is set to 1, and that again instructs TH to reload TL with X again, and then the process continues. So in mode 2, to generate a time delay, you have to remember that you can generate a time delay with only 8-bit numbers, so between 00 to FF. So you load the T-mod value register indicating which timer 0 or timer 1 is to be used, and the timer mode is selected. Then you load the TH registers with the initial count value, okay. Just you load the TH and then you don't have to do anything. Every time it will be auto reloaded. So you load the TH registers with the initial count value, then you start the timer, and then you keep monitoring the TF flag using an instruction like this, JNB TFX target, to see whether it is raised. When TF goes high, you get out of the loop, you clear the TF flag and go back to step 4. Go back to step 4 again. So you don't have to go back to step 2 to reload the TH registers, because mode 2 is auto reload. Okay. So if you see an example here, so let's say I have this crystal frequency. Find the frequency of the square wave generated on pin 1.0 in the following program. So here we are loading timer 1 with mode 2. So this is the combination that we are selecting. So if you look into the T mod register again, so this is your T mod register, and this part is for timer 1. Okay, this is for timer 0, and then out of this 4 bit, this is your M1 and this is your M0. So to load it to mode 2, this combination has to be this. Okay, and everything else is 0. Okay, so this makes 20 hex. So that is loaded here in T mod, and then you are moving a number only to TH1. Okay, you don't need to move anything. Like this is a 8-bit mode, so you move an 8-bit number to TH1, and then you are starting the timer, and then you are monitoring the TF1 until it rolls over. Once it rolls over, it goes to this line where your port 1.0 goes high or low depending on which state it was in, and then you clear the timer flag, and you see you don't have to stop the timer. Okay, you are not clearing the TR1. Okay, in case of the 16-bit mode 1 operation, you are also clearing TR flags. So you are stopping the timer. Here you are not stopping the timer, you are just clearing the TF1, and then you are jumping back to this line. You are not jumping back to this line to reload. Okay, so you don't need to reload as a programmer because it's an auto reload mode. Okay, so this number stays forever in this TH1 and as long as you are using this timer. The only thing is that when TF1 sets to 1 because of rolling over, you have to clear TF1 and then you return back to this line. Once you clear TF1, the timer is already on, so when the TF1 gets set to 1, automatically this number is reloaded to TL1, and you clear TF1 and keep monitoring it again. Okay, so the clock is running. Okay, and your timer is also on. Once it reaches FF, so it starts counting from 5 in this example, counts to 6, then to 7, and so on. Once it reaches 256, okay, it finishes counting, and here at this stage your TF1 gets set to 1, and all you need to do here, when TF1 sets to 1, your TH, which contains 5, that reloads this to your TL, and all you need to do is to clear this TF1, and once you clear this TF1, this timer again starts counting from 5 to 6 to 7 up to 256. So this process continues. So we are asked to find the frequency of the square wave. So that can be done by this. So you start counting from 5. The maximum that you can count is 256. So this 256 minus the initial number times the machine cycle, which is 1.085 because of this clock frequency. So that gives you 272.33 microsecond, which is the high portion of the pulse. And since it is a 50% duty cycle, the period T is twice that. So as a result, you have 544.67 microsecond, and therefore the frequency is 1 over this 544.67. That gives you 1.83597 kilohertz. So you can apply the same concepts and you can find the frequency of a square wave generated on pin 1.0 for this code, and this will give you this particular result. So it starts from 0. Okay, so T80 is loaded with 0 and it's in mode 2. So your timer 0 is in mode 2, so it's an 8-bit auto reload mode. So it starts counting from 0 and to 256, and it repeats 250 times. Okay, because you are generating the delay, okay, multiple times using this DJ and Z. Okay, so basically you count 256, that happens 250 times, and then that into 1.085, which is one machine cycle, and then this is the total delay. The total delay times 2 is your total time period, and that is 138.88 milliseconds. Therefore the frequency will be 1 over this number, and that gives you 72 hertz. So I'll stop here today, and we will continue our discussion in the next video lecture. Thank you.